Hi everyone. Today we are going to have a course called Probability and Statistics. And I'm Le. I'm from Engineering and Technology Institute Groningen. This is my email address. Please feel free to contact me if you have any further questions about probability and statistics. I think most of you have learned this course when you worked as an undergraduate student. And let's say we only have 2 hours for this course, so it's quite a short time, and we don't have uh, enough time to tell you everything about probability and statistics. What I can do in this summer school is to remind you something important in this course, in this field, and maybe you can apply the probability theory and statistics into your further research. First of all, I want to introduce you some general information about this course. We are going to introduce some basic knowledge of probability, some basic definitions of statistics, and some applications like hypothesis testing, parameter estimation, and regression analysis. Because this PowerPoint only have few information about probability and statistics, I recommend you the books here, which are written well. And the first book, it's fundamental and basic, but the last two books can be found with more information about probability and statistics. Okay, let's turn to part one, probability theory. Probability theory is to describe something with probability, and we want to discuss the properties of probability. So we need some basic definitions of outcomes, events, and probability, and we need some basic definitions of distributions for discrete random variables, continuous random variables, and we will also introduce some common distributions. Some famous one like normal distribution, uniform distribution, Bernoulli distribution, some distribution like this. And we will introduce the basic definitions of expectation, variance, and random vectors. In the end, I will introduce you some famous theorems in probability theory, which is important for statistics also. They are law of large numbers and central limit theorem. I will make a comment here about law of large numbers and the central limit theorem. Basically, these two theorems are very complex and it's hard to remember the proof, right? But you need to remember the application of these two theorems and the intuitions behind them. First, I want to say something about law of large numbers. Law of large numbers is to describe some properties when you collect enough data. That is, if you collect more data, you can always approach to the true distribution. This gives you the way to use data to analyze the true world. Yeah, this is very critical, right? And for the central limit theorem, it describes that if you have some average value, it will approach to the normal distribution. Let's say it just describes why the name of normal distribution is called normal distribution, because it's quite normal if you have many if you have some average value from distributions, any distributions like uniform distributions, uh, the average value you collect every time will will follow the distribution of normal distributions. Yeah, this is why we are interested in normal distributions. Okay, so let's turn to the first part, some basic definitions. We call a set of outcomes of an experiment as a sample space. This means the sample space contains all the possible outcomes. And we call a subset of the sample space an event. Two events A and B are disjoint if they have no elements in common. Yeah. I give an example here to show what is a sample space, what is an event, and what do I mean by disjoint. If you have a dice and you throw it many times, all you can get, the number all you can get is from 1, 2, 3, 4, 5, 6. The 6 numbers give us a set, which is sample set in this example. And if you want an even number, the set of the even number is an event. If you want another set, let's say an odd number set, as you can say directly, the odd number set is disjoint from the even number set. So these two events are disjoint. Sometimes I will use events and sometimes I will use sets. You should understand these two words are similar in probability theory for now. We have some axioms on probability. The first one is non-negativity. This is very easy to understand. You will never have a negative probability, right? And the second one is normalization. It means that if your sample space is fixed, all of the events happens in the sample space. And we have another axiom called additivity for disjoint unions. It means that if you have one event and you have another event, they are disjoint. The probability of these two events, it's just the sum of the probability of the two events. Yeah, it's quite simple. And an important law for the set computation is introduced here. It's called De Morgan's law. You should remember this. It describes some calculations between sets, specifically with complements. We have some calculation results here. If you use the axioms in the last slide, specifically with additivity and normalization, you can get the following result. And I have a question here, how to calculate the probability of the union of A and B and C. Yeah, the answer is quite simple. You can first calculate the probability of the union of A and B, and then calculate the union of A and B and C. And you will get the result here. Yeah, it's a little bit complex result, but if you have a graph, you let a circle to describe the set A, and you have another circle B, not circle, you have, let's say, Yeah, you have a ball. Yeah, you have a ball called A, you have a ball called C, you have a ball called B, and you put them together, you will see this result immediately. Okay, here are the definitions for conditional probability. The conditional probability is quite useful and common in real life. Assume that you have lunch at noon. The probability of your supper time at 4 p.m., let's say uh, it's quite impossible because you have lunch at noon and you are not going to be hungry at that time, right? But if you don't have lunch at noon, the probability of your supper time at 4 p.m. is quite possible because you are going to be hungry. So the conditional probability just describe the probability after you have done something. Yeah. In the definition, it says that the probability of A conditional on C is equal to the probability of the intersection of A and C divided by the probability of C. It is worth noting that the complement rule still works for conditional probability, and for three events, we have a similar expression for the conditional probability. The independence is defined here. We say two events are independent if the probability of the intersection is equal to the products of the probability. And for more events, more than two, the situation is a bit complex. You cannot just check that the probability of the intersection is equal to the products. You need to check more equations. In general, establishing the independence of m events requires checking the m power of 2 equations. Yeah, because you need to check every complement and you need to check every combination, and after some calculations you will realize that you need to check the power m of 2 equations. Let me introduce you some useful results here. Maybe you can use for calculations and other stuffs. The first one is multiplication rule. It means that you can calculate the intersection of different events with conditional probabilities with the products of conditional probabilities. And the second one is the law of total probability. It describes that if you want to calculate the probability of the event A, but you don't know, but you only know that the probability of, let's say, A conditional on C1 and A conditional on C2, and you can calculate in this rule. And we want to introduce the Bayes rule here, which is important in Bayes inference. It's just calculated directly with two conditional probability. Okay, after defining so many things, we are going to describe the distributions. So what is distributions? The distribution describe one thing. What is the possible value of your random vector of your random value? Sorry. Let's say it more formally. A discrete random variable is a function that takes on a countable number of discrete values. So the probability mass function of a discrete random variable is a function R to an interval defined by this equation. So for any set, you only need to add all the mass function on this set. And the cumulative function f(x) of a discrete random variable x is a function defined by the probability of the random vector is less than a given value. And it should be noted here, the cumulative distribution function of a discrete random variable is a piecewise continuous from the right. Yeah, it's not the same as the continuous random variable. I mean, the cumulative distribution function of a random continuous variable, it's a continuous function, but for a discrete random variable, it's just piecewise continuous from the right. If you learn it a bit further, you can describe this with Lebesgue-Stages measure. It will tell you that if you have this kind of measure, you can combine the discrete random variables with continuous random variables together and consider them in under the same framework. Here is an example about a discrete random variable. Yeah. Yeah, you have some discrete random variables with some values, and for each value you have a probability, and with this kind of setting you will have discrete random variables and its distribution. Okay, this is a definition for the continuous random variables. A random variable x is called continuous if some function, let's say it's a probability density function for the random variable, and the probability of x, which is larger than a but less than b, is equal to the integral of the density function. In particular, the cumulative probability function is equal to the integral from minus infinity to a given value. Okay, let's introduce some common distributions which you can check if you remember it or not. It's quite important in your analysis in probability theory. The first one is called Bernoulli distribution. The Bernoulli distributions describe a random variable with two values. One is in x1 and another value is x2. x1 is with probability p and x2 is with probability 1 minus p, right? And we give the expectation here and the variance here. Also, for a general one, which is a general version of Bernoulli distribution, is called binomial distribution, and the probability mass function is given here. You can say why we call this general one, because expectation and variance and the distribution is just the same as the Bernoulli distribution when you choose n equals to 1, right? And we call x has a geometric distribution if it follows that its probability mass function is equal to p times the power k minus 1 of 1 minus p, and expectation is 1 divided by p, and the variance is 1 minus p divided by the 2 power of p. And we have a we also introduce a Poisson distribution here, which is important in stochastic process. It describes that if you have some event may be happening, has the Bernoulli distribution in a period after many times, after long enough time, you will have a distribution of how many times it happens as Poisson distribution. And the uniform distribution is given here. You can check here. You should remember that the expectation and the variance. And we also introduce exponential distribution. Actually, the one of the important properties of the exponential distribution is that it's memoryless. It means that if you have a fixed value x and y which are larger than 0, the probability of x larger than x plus y conditional on x is larger than x equals to the probability of x is larger than y. The expectation of the exponential distribution is 1 divided by lambda, and the variance is 1 divided by the 2 power of lambda. We are going to discuss the most important distribution in probability theory and statistics. It's called normal distribution. It has another name called Gaussian distribution because it is analyzed by Gauss, and it has many beautiful properties, even though its probability density function and cumulative distribution function is very ugly. But it's quite normal, as we will see in the central limit theorem. You should remember the probability density function. For the cumulative function, we don't have a explicit form, so you only need to remember the probability density function, which is very important. And for the standard normal distribution, we mean that the distribution with 0 mean and variance is equal to 1. And you should also remember that the probability density function is symmetric about x equal to 0. Yeah, we have given some expectations and variance about common distributions, but we don't introduce you the formal definitions of expectation. Here we give some formal definitions of the expectation and variance. Expectation is something very easy to understand. It just describes the average value of your random variables. If you have a random variable, one way to calculate the expectation is to plus the products of the value and the probability. It will give you an average value in this way. And the variance it's similar to the expectation. It actually is defined by expectation. It describes how large the deviation is for a random distribution. If you have a random distribution which is equal to a constant, for the probability for a constant in this random variable is equal to 1, you will not have variance because there is no deviation, right? If you have, let's say, a large deviation, it means that your random variables can be distributed in a very distributed way. Yeah, it may be at this time, if you check this for 2 times, at the first time it may be 1, and at the second time it may be 100, and this is the meaning of the variance. If we have 2 independent random variables, the expectation of the 2 independent random variables are also independent. And we have the expectation on the linear transformation. Let's say the expectation is linear actually, and for the variance it's not linear, but if you add something to the random variables, the variance is the same. But if you multiply something to the random variables, the variance is the power 2 of what you have multiplied. The expectation and the variance of random variables is given here. Specifically, if you have independent variables, for the variance case, the covariance will disappear. So for independent random variables, the variance of the sum of the independent variables is just the sum of the variance of each random variables. Here, let's review some definitions of joint probability functions. The joint probability mass function of 2 described random variables is a function defined in this way. It is worth noting that the joint probability mass function also satisfies the non-negativity, the normalization, and for the joint probability density function, it also satisfies the non-negativity, the normalization, which are the same as the distribution function. And for the cumulative distribution functions of joint distributions, it defines in a similar way. Here we want to point out the independence property here. If we have 2 random variables, x and y, we say that they are independent if their cumulative distribution functions are independent. And we say the continuous random variables are independent if their probability density functions are independent. And we have some necessary and sufficient conditions for independence. We call random variables x and y are independent if and only if they satisfy separable joint probability density functions and a rectangular feasible region. Also, we can define some variance here, which is called covariance between random vectors, random variables x and y. It describes the relation between x and y. If x and y are positively correlated, the covariance of x and y is larger than 0. And when x is larger than the expectation, it tends to be true that y is larger than the expectation. On the other hand, if x is larger than the expectation, we tend to observe that y is less than the expectation, then x and y are called negatively correlated. and the covariance of x and y is less than 0. If covariance of x and y are equal to 0, then x and y are independent. Are uncorrelated. Sorry, are uncorrelated, not independent. The correlation coefficient is defined to be 0 if the variance of x and or y is equal to 0, and otherwise it's defined by this way. The correlation coefficient is dimensionless, and it is invariant on the linear transformation of x and y. This means in some situations, under some situations, it is invariant with coordinations. So it is important to use this. It is to analyze some physical outputs, and let's say the outputs of some experiments. It is worth noting that the correlation measures the directional dependence between x and y. X and y are most correlated if x is equal to y, in which case the correlation coefficient is equal to 1. If x is equal to minus y, in this case, the correlation coefficient is equal to minus 1. Here is a definition for the random vectors, which is very simple. It's just the joint distribution of many random variables. And we also have some expectation and a covariance here. It should be noted here that the variance is going to be a covariance matrix because the vector is an n-dimensional vector, and you will have a matrix to describe the correlation between the coordinates in each random vectors. And you can check that the covariance matrix is symmetric, and if the random vectors are linearly independent, you will only have a diagonal matrix as the covariance matrix, and this covariance matrix is positive definite. We call a sequence of random variables is independent and identically distributed if the random vectors in the sequence are independent and all have the same distribution. And the sample mean for this independent and identical distributed random variables is defined by this way. It's just the average value of the random variables. If the expectation and the variance of the random variables are mu and the power 2 of sigma, then the expectation is of the average value, the sample mean is mu, and the variance is the power 2 of sigma divided by n. The variance is very important here because we will use it again and again in statistics. You should remember the variance is not the power 2 of sigma, it's the power 2 of sigma divided by n. But why? We will show this in statistics why the variance is a little bit different from the original distribution. Okay, here we are going to talk something about law of large numbers, but feel free, it's just some introduction, so you don't need to remember anything of the proof or anything here because the proof for law of large numbers is a little bit complex. We are going to introduce some definitions, and you only need to remember the definitions. First, it's a weak law of large numbers. If we have a sample space and the sample space will approach to the expectation, I mean the probability of the sample space will larger than the will be a bit larger than the expectation is equal to 1. Yeah? For a strong law of large numbers, the probability of the limitation is equal to 1. It's a little bit different. The difference is the location of the limitation of the limit signal. Yeah, if yeah, it's hard to analyze this explicitly, but yeah, you can check for the book written by Duret. With the book's name is Probability Theory Examples. You can check these books for the details, because these two conditions, maybe they look similar and they describe something maybe similar in physical world, but actually in mathematics it's quite different. And generally speaking, with law of large numbers, in combination with simulations and histograms, we can recover the probability of any particular event and hence recover the Hoover probability density functions. Here we just give the simple versions of law of large numbers. The conditions for strong law of large numbers are more strict than weak law. For the proof, one can refer to that book. Yeah. The central limit theorem says that if you have a finite variance, then as an approach to infinity, the distribution of the given random vector of the given random value is converged to the Gaussian distribution. This theorem states that the normalized distribution of sample mean will converge to the Gaussian distribution. So it is a key concept in probability theory because it implies the probability and statistics method that works for normal distribution can be applicable to many problems involving other types of distributions. Okay, let's turn to part 2, statistics. Statistics is quite important in experiment because probability theory is just the fundamental of the statistics, but for application, statistics is more important. If you have some data outputs from an experiment, statistics gives you some way to analyze the data, to analyze if the data is correct. Let's say if it follows it, if the data, whether the data verifies what you have proposed. Using statistics way, you can establish the connection between the real world and the experiments, right? So our content is divided by 5 parts. The first part is about sample mean and sample variance. I think you should remember that the sample variance is the variance of a distribution divided by n. We will illustrate this by calculation, and we will discuss something about empirical distribution. Empirical distribution is just something that you get from the experiment. It describes the data's distribution. And we will discuss something about hypothesis testing and parameter estimation, regression analysis. These are simple applications of statistics. the sample variance of the sample is given by this. So y is n minus 1 instead of n. I think all of you have learned this, but why n minus 1? If you remember, you can calculate this, right? Yeah, I will give you this question, and maybe you can calculate it first, and we will give the answer after this slide. First, we want to point out that the factor n minus 1 leads to an unbiased estimator, but n does not. So the sample standard deviation of the sample is given by the root of the sample variance, but it should be noticed that the sample standard deviation is biased estimator of the true standard estimation deviation. It's standard deviation sigma. What do I mean by unbiased? It means that if you take expectation on this variance, the expectation on the variance is equal to the true variance of the distribution. If, let's say, if the expectation is equal to the true variance, it is unbiased. If your expectation is not equal to the true variance, it is biased. In this case, if we have n minus 1 instead of n, we will have an unbiased estimator for the variance, but for the deviation, it is not. It means that the expectation of the standard deviation here is not equal to the true standard deviation sigma. So why divide n minus 1 instead of n? We have an answer here. First, we calculate the expectation of the variance. Yeah. And we expand it, and we use the variance of of the sample variables, right? We use the variance of the sample mean. Sorry, we use the variance of the sample mean here. And then we will get that expectation of the variance is equal to the true variance. A sample or a random sample is a collection of identical independent distributed random variables. In most of statistics, we view our data as realizations of a random sample. A statistics is of any function of the sample. For example, sample mean is a function of the sample, and the sample maximum is also the function of the sample. And also, you will have sample minimum, such things like that. They are just the functions of the sample. The empirical distribution is a function that's defined in this way. It describes the number of the sample in the period from infinity minus infinity to a divided by n. And the law of large numbers tell us for every epsilon which is larger than 0, the limit of the probability will approach to 0. It means that for large n, the empirical distribution function approach to the true cumulative distribution function, which means that your data from experiments is useful. You can use the data to simulate the true world, right? It's very interesting. Okay, we will teach a useful application, hypothesis testing. It's just some standard it's just some standard expansion of statistics. Hypothesis testing deals with using data to figure stuff out about an unknown parameter theta of the sample's distribution. In hypothesis testing, we want to choose between two different statements about sigma. For instance, sigma is equal to 5 versus sigma is equal to 10, or sigma in a period with sigma is in another period. And in this chapter, we will discuss something of how to construct a good hypothesis test and how to compare the quality of two tests. As in the previous sections, X is the sample, so its ID, and whose distribution depends on a parameter theta. Here, the parameter theta, you can think of it as something in the real world. Let's say, for example, if you have theta is equal to 0, you will say, I have lunch. If your theta is equal to 1, you can say, I don't have lunch. And in this way, we observe the time of the supper and we estimate that whether you have lunch or not. There are some standard setting ups in hypothesis testing. The first one is null hypothesis. This models our current beliefs about theta. It should be noticed that we always have a current belief and we believe this belief. Like, I always believe you have lunch because you seldom don't have lunch. And we have another belief, an alternative. It is named by the alternative hypothesis. This models some different beliefs about theta. Generally, hypothesis testing is conservative in that we require very strong evidence to reject H0 in favor of H1. Our inclination is to stick with the status quo. A hypothesis with omega I is equal to the set of theta I is called simple. A composite hypothesis is one that is not simple. Omega I contains more than one variables. We call the set of all possible parameter values omega 0 and omega 1 are disjoint subsets of omega. A test static Tx is some function of the sample that we use to check whether or not we reject the null hypothesis. The critical region is a set of all values that cause us to reject H0. Given a test statics, if it is in the region C, we will reject the null hypothesis. We will use the test statics to construct this region C. In the definition, the set I is critical, is constructed somehow by the tester. The quality of a test depends on the choice of the C, also R. We call the rule reject the null hypothesis if X belongs to the region C is equal to reject the null hypothesis if Tx belongs to the region R, the decision rule. A type 1 error is a false rejection of non-hypothesis. Formally, the probability of type 1 error is alpha equals to the probability of rejection the non-hypothesis conditional on H0 is true. If the non-hypothesis is simple, then alpha is a constant. If the non-hypothesis is composite, then alpha is dependent on the parameter value theta. Also, we have a type 2 error. It's a false acceptance of non-hypothesis, and it's defined in a similar way. If the alternative hypothesis is simple, then beta is a constant. If the alternative hypothesis is composite, then beta is dependent on parameter theta again. Since we are conservative, controlling type 1 error is most important because we want to make it small because we trust the non-hypothesis, we want to accept it. So we must control type 1 error. The significance level or size of a test, denoted by the bar of alpha, is an upper bound on alpha. The significance level is a specification set by the tester. This test must have a significance level no higher than the bar of alpha. Typical values of bar of alpha are, let's say, 0.05, 0.01. For a simple non-hypothesis, we can choose the region C such that alpha is equal to the bar of alpha. For a composite one, we can choose the alpha theta is less than the bar of alpha. A test with the significance level bar of alpha is called a size alpha bar test. The power function of a test is the probability of rejecting the non-hypothesis given that the alternative hypothesis is true. Formally, eta theta is equal to the probability of reject H0 condition on H1 is true, and is equal to 1 minus beta theta. When considering two tests of size alpha bar, the test with a higher power is better. If the power of a size alpha bar is at least as high as the power of any other set alpha bar test, then it's called a best test of size alpha bar. Consider the test of size alpha bar, H1 versus H1 versus H0 with critical region. Then the p-value of the test is equal to the probability of Tx larger than Tx conditional H0 is true. So, but the question is, why do we care about the p-value? Well, we can use it to make our decision. We reject the non-hypothesis if the p-value is smaller than the bar of alpha, the alpha bar, and we accept the non-hypothesis if the p-value exceeds alpha bar. Another important application of probability and statistics parameter estimation. If you have a model or a distribution, like Gaussian distribution, you want to estimate its mean value. You know the variance, but you want to estimate the mean value, the expectation. A simple way is to collect all the sample data and calculate the sample mean and use the sample mean as a parameter estimation. But is this estimation effective? This is a question. Is this how do we analyze the parameter estimation? How do we say a parameter estimation is effective or not? This is the analysis core of the parameter estimation. Let P become a distribution that generates data. We denote the sample data as X. If we want to use the sample data to recover the true information about distribution, for example, the mean of the Gaussian distribution, we need to estimate the distribution parameter. How to construct a good estimator and how to evaluate the quality of the estimation is a core part of this chapter. First, a point estimator is a statistic suitably designed to estimate population parameter theta. A point estimate is a realization of a point estimator. The difference here is that the first one, a point estimator, is constructed by a function, but the second one is constructed by data. So it's a realization. The bias of an estimator is defined by the expectation minus the true parameter. If the bias is equal to 0, we call this estimator unbiased. A biased estimator has a systematic tendency to overestimate or underestimate the true parameter theta. So in practical world or in practical applications, in most cases, we don't want a biased estimator. We want an unbiased estimator instead. For a vector-valued estimator of parameter vector theta with estimation error, the bias is given by this. Note that the expectation may be taken over different distributions in the Bayesian or non-Bayesian approach. An estimator is constant if for large n, the estimator is almostly or approximately equal to theta. More precisely, if it is constant, the limit of the probability that it's not equal to theta is equal to 0. Note that if the estimator is constant, then as n approach to infinity, the bias will approach to 0. Let theta 1 hat and theta 2 hat be two unbiased estimator of theta. Then we say that theta 1 hat is more efficient than theta 2 hat if for all theta, the variance of theta 1 hat is less than the variance of theta 2 hat. Yeah, remember that the variance describes the deviation. If the deviation is less, it means our estimate is stable, so we say it's more efficient here. And this is to say an estimator with smaller variance is more efficient. The mean squared root error of an estimator theta hat is given by the expectation of the 2 power of theta of the square of theta bar minus theta. And after some calculation, you can separate it as the variance of theta hat and the bias, the square of the bias. If it is, the theta is a random vector, not a random vector, it's a vector instead of a scalar, you can have a similar definition for the variance and for the mean squared error. The mean squared error of an estimator measures its spread around the true parameter value. We say that theta 1 hat is better than theta 2 hat in the mean squared error sense if the mean squared error of theta 1 hat is less than mean squared error of theta 2 hat. Note that in some cases, a biased estimator with a small mean squared estimator mean squared error is preferable to an unbiased one. This means that even though we like unbiased estimator, an unbiased estimator may be worse in some cases. It is almost never possible to find an estimator that's optimal in the mean squared error sense. But however, we can find some estimator with the smallest variance. What does this mean? This means if we fix the bias is equal to 0, I mean we want an unbiased estimator, and under this condition we try to let the variance as small as possible, then this calculation is possible. But for a general calculation, we want to minimize the mean squared error. It's calculation impossible. A famous parameter estimation way is called the maximum likelihood estimation. It is founded by Fisher, and we just introduce the likelihood estimation here. First, the likelihood function of a dataset is sampled from a distribution with unknown parameters, and the product of the distributions of the probability mass function or probability density function, it's called the likelihood function. No. And the log-like likelihood function, it's just the lowing of the log likelihood function. Because the lowing function is just a monotone function. So if we want to maximize the likelihood function, we can just maximize the lowing likelihood function, right? For most cases, for most distributions, you will always find a maximum point for the log likelihood function. So when finding the MLE of the theta involves differentiation, the log likelihood function is often easier to work with the likelihood function, because the log of the product is sum of the logs. The maximum likelihood estimator of a parameter vector is given by this formula. We just maximize the log likelihood function or maximize the likelihood function. In general, theta hat ML may be biased or unbiased. Theta hat ML is always constant, and as n approaches infinity, theta hat ML has the lowest possible MSE among unbiased estimators. This means that theta ML attains a Cramer-Rao bound. There are many other ways to estimate parameters, for example, Bayesian estimation, and minimum square estimation, and robust estimation, such things like that. But most of them, except for Bayesian estimation, most of them, they will need a function, and they will minimize a function to get an optimal parameter. For minimum square estimation, it minimizes the trace of the square. For robust estimation, it minimizes the one norm of the error. Yeah. But Bayesian estimation is not. It's not like this. It's here is the final part of the statistics. We want to introduce you the regression analysis. This is a little bit similar to the parameter estimation. If you have a lot of data and you want to find the relationship between datas, let's say you have X data and Y data, you want to find the relationship of X data and Y data. a useful way is to use regression analysis, and the most simple way is linear regression. So we consider the most simple model here. You can consider other model like logistic or other models to do regression analysis, but here we consider the most simple one. We assume that there are two parameters to be approximated or to be regressed here, because there are always noises in regression analysis. Our aim is to make the effects of the noise as soon as possible. It means if there is no noise, we can solve the equations and we can get accurate beta 0 and beta 1. But there are some noises in this process. We cannot get the accurate ones. Instead, we can think the noises are very small, and if the parameters make the noise as small as possible, then it's a good parameter because it will give as accurate as it will give prediction as accurate as possible, right? So if we define energy function Q here, and we have beta 0 and beta 1 in this energy function as some variables, we can minimize this kind of functions. A simple way is to use the square. We just use the sum of the square and we minimize this sum of the square. We can get the estimation of the beta 0 and beta 1, and this is how we do with regression analysis. It's just a simple application of parameter estimation. Furthermore, since we have a statistics Q here, one can refer to the hypothesis testing. If you have some hypothesis of beta 0 and beta 1, for example, you believe that beta 0 is larger than 5 as non-hypothesis, you will have another alternative hypothesis like beta 0 is less than 1. You can do hypothesis testing here. One can also use another kinds of energy function like maximum likelihood or other kind of functions, and you will get different regression results. And how to choose energy function is based on your experiment. And since we only give a linear model here, actually one can use more general model like polynomial or other models like this to get more complex results. And also for simplicity in your experiments, maybe linear model is the simplest model. So in your experiments, if you have no idea, you can try to use linear regression. But if you have ideas about what the model is like, you can use other model to do regression. Yeah, that's all. Thank you.